Hi guys, my name is Zach. I work here at the Radiation Science and Engineering Center, and today I'm going to tell you how a nuclear reactor works. There are two types of reactions that can occur inside of a nuclear reactor. One is fusion, where we take two very small atoms, typically two hydrogen atoms or a hydrogen and a helium atom, and we smash them together until they form one larger atom. The other type of reaction that happens inside of a nuclear reactor is fission. This is what happens inside of our reactor at Penn State.
This is the reactor's core, where all the craziness happens. In there is the nuclear fuel. Uranium pellets.
The fuel that we use is uranium-235. When uranium-235 is hit by a thermal neutron, it absorbs that neutron and becomes uranium-236.
That makes the atom unstable and it splits into two. This process is called
nuclear fission.
That process releases energy and also releases more neutrons. Those neutrons are free to interact with more uranium atoms inside of the fuel.
It releases a lot of energy and more sassy neutrons, which smash into other aliens with cowboy hats over and over and over again. That is called a chain reaction.
To help control this reaction, we use something we call control rods. Those control rods are made of a material called boron. Boron absorbs neutrons readily. So when you insert the boron into the nuclear reactor, you use that boron to absorb the neutrons so that they cannot interact with uranium atoms. This is a 1/3 scale model of the reactor that we have at Penn State. Each one of these represents one of our fuel rods that are inside of the core. Compared to this, our real reactor is this size. Also here, we can see the size of a control rod in comparison to one of the fuel rods. You can see it's about twice as long as the fuel rods. When the control rods are inserted into the core, the boron, or the top portions of the control rods, are lined up with the nuclear fuel. Whenever you take the control rods out of the core, you release that boron, allowing the neutrons to interact with more of the fuel, and also in 3 of our control rods there is more fuel at the bottom. So not only are you taking boron out of the core and allowing those neutrons to interact rather than being absorbed by the control rod, you're also introducing more uranium atoms into the core for them to be able to fission. Now I'm going to take you into the control room. In this screen, you can see a video of the control panel inside of the control room. There are 2 screens. The screen on the left has an indication of where the control rods are, and on the screen on the right has an indication of power level. As CJ, our reactor operator that day, pulls the control rods out of the core, you'll notice that the power on the right-hand screen is going to go up. In the bottom right-hand corner, we have a video of the reactor. As the power levels increase, you can see the reactor get brighter and brighter blue. That blue glow is something we call shrink-off radiation. Shrink-off radiation is caused by particles moving faster than the speed of light in water. So, speed of light in water is much slower than the speed of light in a vacuum. We're obeying all the laws of nature. However, when those particles surpass their own light speeds, you get something similar to a sonic boom, only instead of a jet or a car moving faster than the speed of sound and running into their own sound waves, you have particles, electrons, moving faster than the speed of light and running into their own light waves. This process puts off this blue glow, which is proportional to power. So that's why you saw the blue glow get brighter and brighter as the power increased. If you were able to join us in person today, what you would have seen is the reactor giving off this blue glow. We would have went to a power level for you and let you into the reactor bay. We looked over the side of the pool. The reactor is about 20 feet under the surface of the water, and this is what you would have seen. I took a few videos from the side of the pool wall and compiled them together here at different power levels for you to get a kind of an idea of what it would be like to be there today. Hopefully we'll be able to invite you back in person sometime very soon. One other thing we could have done for you today is something we call a pulse. A pulse is when we take the reactor from about 100 watts of thermal energy and we bring that last control rod that is out of the core very quickly. What happens there is that the power goes from a very low level or a very dim bright light to a very high power level very quickly. In fact, it goes from about 100 watts to about 350 million watts in about a quarter of a second. The reason why we can do this is because of something called a moderator, which is built into our fuel and is provided by the water in a typical power reactor. What a moderator does is it slows down the neutrons after they're born out of the fission reaction and before they are captured by the next generation of uranium fuel. When neutrons are ejected from the fission reactor, they're moving much too fast to cause fissions. They just zip right by the next uranium atom, and if they do that, they can't be absorbed and cause another fission. Imagine you're on a golf course and you're trying to make a quick putt. If you hit the ball too hard, well, you get the idea. Instead, what we need to do is we need to put things in between where the neutron is ejected and where it's going to be absorbed, particularly hydrogen atoms. Once they bounce off enough hydrogen atoms, they'll lose enough energy that they are slow and can be absorbed by a uranium atom and cause another fission. At the Penn State Trigger Reactor, we have zirconium hydride as a moderator, which is built into each one of our fuel rods. When we perform a pulse, we go to 100 watts using the 3 control rods that are followed by fuel and take the stopper for the last control rod that is held up with air pressure to a specific point. When we eject that control rod, the power goes up very quickly. And with the power going up, so does the temperature. The increase in temperature makes it so that the moderator cannot moderate as well. And what we have at the peak of the pulse is a lot of neutrons that cannot interact with more fuel because they're moving too fast. And that turns the reactor power back around and shuts it down before we can physically do anything to stop the reaction from running away. And that's the reason why we at Penn State can perform this experiment. As you can imagine, with the pulse happening so quickly, it's pretty difficult to get on camera. So what I've been sharing with you is some high-speed video footage that we got from WPSU when they came by the reactor about 12 years ago. Last thing I'm going to show you today is the pulse operation from inside of the control room. You're going to hear a 5, 4, 3, 2, 1 countdown from CJ before he applies air pressure to that last control rod.
The reactor will be pulsed in 5, 4, 3, 2, 1.
So you probably heard the air pressure kick the control rod, the transient rod, out of the reactor core, and at that time you can see on the right side of the screen the power levels shoot up very dramatically. If you're paying attention to the left screen, you would be able to see that the 3 control rods that are followed by red or followed by fuel were held up, where the last rod that was followed by blue or followed by air was still down until CJ pressed the button. We're going to show you the high-speed data collection now. So over on that left side of the screen we're zooming in on, we can see some of the data that was collected during that particular pulse. We started at 100 watts. We ended at 383 megawatts. That entire bottom of the screen, that entire x-axis is 216 milliseconds. The time from one half of the height of the peak to the other side of it, about halfway down, what we call the half height width, is only 20.7 milliseconds. So this particular pulse was done and over with in less than a quarter of a second. Thanks for joining us today for that virtual tour. If you have any questions, feel free to shout out to me. My name is Zach. I work here at the Radiation Science and Engineering Center, and have a great day.